Professor Anna Moditi, Executive Dean, Faculty of Science. Professor Charles Sheppard, our inductee this evening. Professor Aletta Prinsloo, our respondent, also a physicist and an experimentalist here at UJ. Senior leaders of the university, members of Senate and other academics, distinguished guests, students, and all those who join us online. Sanbonani, Huyenant, good evening, Tobela. It is indeed a great honor and special privilege for me to welcome you to the Professorial Inaugural Lecture of Professor Charles Sheppard. As I do so, I wish to express a warm welcome to his loved ones, special guests, and colleagues. It is indeed a proud and joyful, yet a landmark moment for all of you, for Professor Sheppard, for us here at UJ, for higher education in South Africa and beyond. This is particularly noteworthy as we celebrate 20 years of UJ this year. Since the merger in 2005, we have come to exemplify how excellence and access are not mutually exclusive in higher education. In the spirit of innovation and social responsibility, UJ has pushed boundaries and prioritized research, technological advancement, and community engagement. It is against this backdrop that we welcome you to the Professoriate, a community of scholars dedicated to UJ's ethos of academic excellence while making a tangible impact on society. The inauguration of professors, ladies and gentlemen, is a public ceremony in which newly appointed professors are inducted into office by the Vice Chancellor, who has requested that I represent him today, and deliver their inaugural addresses. The ceremony has its roots in medieval university and serves multiple purposes. First, it is an expression of welcome and an entry for new professors joining the circle of colleagues who are already professors. Secondly, it provides a platform for professors to display their expertise in the discipline and showcase their research. In the colonial traditions subscribed to by many universities, assuming the role of professor refers to the gown and the cap. Once we have listened to the inaugural address, the gown denoting the professorship will formally be assumed. Today, we gather here, colleagues, to witness Professor Charles Sheppard's entry into the illustrious community of scholars at our university, to celebrate his contributions to the discipline and ultimately his impact on society. Professors provide a university with its identity, character, academic legitimacy, and integrity. The inaugural lecture is a rite of passage following the confirmation of the appointment of a person as a professor. So this evening we will listen to Professor Charles Sheppard as the gown goes to town. And by this I mean that the power of the inaugural address is when the expertise is showcased beyond the corridors of this university and reverberates with society. It stands out as a moment of pride for the incumbent, the family, the fellow scholars, the university, and ultimately society. In the past, several philosophers and scholars have defined universities using very narrow conceptualizations. For example, the search for truth, for universal knowledge, and even as instruments serving the purpose of the economy or being utilitarian in nature. Through our work in research at UJ, I hope that we can break out of these narrow conceptualizations and reflect on the university as contributing to the public good, working towards societal impact. What is the role of the intellectual then? Edward Said, in one of his articles, defines the role of the intellectual as, and I quote, one who commands a vast knowledge of a specific discipline, one who is rigorous in the analysis of literature, who views being an intellectual as a vocation, and who functions as a kind of public memory to recall what is forgotten or ignored, to make the connections that are otherwise hidden, and to provide alternatives for mistaken policies, end quote. It remains then for us as a university with a Pan-African vision to derive our mandate as intellectuals and as professors. And importantly, how do we embrace the role of a professor as a disruptor while continuing to be a flagship carrier of our disciplines? This evening, ladies and gentlemen, we will listen to Professor Charles Sheppard as one further step in the journey of being a professor. This is a journey which does not conclude once this lecture has been given. Notwithstanding, this inaugural lecture does create an opportunity for a self-reflective pause in the journey of the professor. And so with that, ladies and gentlemen, let me invite our Executive Dean, Professor Anna Moditi, to introduce Professor Charles Sheppard. I thank you. Ke a leboga, ke a bonga pae, dankie.
Good evening. Sani Bonan. Goeienaand. Dumelang. Vice Chancellor Functionary, Ms. Nolwasi Mamurare, please allow me to observe protocol. Ladies and gentlemen, it gives me a great pleasure to introduce Professor Charles Sheppard. Charles matriculated from the, and this is the Sotho version, Hoër Technisch School, Jan Viljoen, in 1994, and started with university studies at Rand Afrikaans University in 1995, intending to become an electronic engineer. During his second year of study, he consciously chose to change to a BSc degree with chemistry and physics as the major subjects. He graduated with a BSc degree in 1998 and a BSc honors in physics in 1999. His master's and doctoral studies followed, focusing on thin film solar cell materials, initially in the master's project on amorphous silicon, and in the postgraduate studies of copper, indium, diselenite-based solar cells. He graduated with a doctoral degree in 2008. During the early stages of his PhD, the Department of Physics at RAU/UJ only had 5 lecturing staff members. Because of the language policy changes, the department had to teach English and Afrikaans. Charles was approached to assist with lecturing some of the undergraduate and STEM modules became permanent and STEM modules under the guidance of Professor Prinsloo and Professor Alberts. In 2001, his appointment became permanent when he was appointed as a junior lecturer. Since then, he has lectured on most of the undergraduate courses in the department, except for third-year modules. Charles started teaching advanced electromagnetism, an honors module, from 2014 to 2017, and the advanced solid-state physics in 2023. As his experience as lecturer grew, his post levels advanced through the various levels from junior lecturer in 2001 to associate professor in 2019. He had a post level until he had this post level until 2024. In addition, in 2017, he became deputy head of department with a focus on teaching and learning aspects within the department. He remained the deputy head of the department, teaching and learning, until 2021. As part of his academic responsibilities as a lecturer, Charles has served on various committees as a reviewer, moderator, and examiner of local and international modules and degrees. As authors and co-authors, they presented their research at 39 local and 49 international conferences. To date, 67 international journal publications have been published by postgraduate and international collaborators. Charles helped train 1 MPhil, 2 MScs, and 4 PhDs to completion in supervisory or co-supervisory roles. Currently, there are 4 doctoral projects in progress under his guidance. He has also acted as supervisor for 3 postdoctoral fellows during this time. In terms of funding, Charles was successful during the doctoral studies in applying for Tutuka funding in the doctoral track. And after his doctoral degree he has successfully applied for various travel and training grants at the National Research Foundation and the University of Brest in France, where he used the funding to visit and do research work as their collaborator. One of the most successful funding applications was the application to the National Research Foundation with the National Equipment Procurement Program in 2014. In his application, his primary responsibility was to provide and motivate the technical aspects of the physical properties measurement system. The NEP application was valued at about 15 million rands. Charles currently holds a C2 National Research Foundation rating after being re-rated at the end of 2024. He also holds a professional support title, Professional Science and Natural Science from the South African Council of Natural Scientific Professions since 2017. Ladies and gentlemen, Professor Charles Sheppard.
Good evening, ladies and gents. I don't like standing behind that, so yeah, probably have to say protocol. I teach in front of the class, so yes. Yeah, let's jump into this and start with it. I started with this fascination of chromium in the sense that I thought it will give me a wide sort of berth to discuss chromium in general. But in actual fact, looking at this, if we just look at it, it actually asks a question. Why are we still doing research on chromium even after 45 years? And tonight I hope to sort of give you a flavor of why we are still studying chromium. In this case, we call this a simple metal, and you'll see it's only simple in structure. Very complex things actually happen with this metal depending how you use it. So, further ado, so if we jump into this, you do a little bit of search and you say, okay, let's use our AIs nowadays, that's technology. And you ask, okay, chromium, what happens, it tells you something about chrome. It says it's a chemical element, it's hard, it's steely gray. It is element 24. And then it goes on and it repeats itself again. Important of chrome, of course, in the sense is you find it actually in 2 forms. One is trivalent, which is actually very important to human beings, very important to how our bodies actually look at glucose and effectively insulin. And even here, I got intrigued to look at it. And even there has been 50 years of study already, just in the medical use of it. And then, of course, let's say there's not always good, there's also some bad. In industry, you see mostly hexavalent chrome when they only manufacture clean stainless steel and not stainless steel chrome itself. And this is effectively chrome 6, which is dangerous in some large quantities to human beings. And of course, there's quite a lot of uses. We'll jump into some of the uses now. a bit more detail. So if we look at just chromium in general in the country, where does it place? Well, actually South Africa produce about 83% of the world chrome ore that we of course sell out. And then at very expensive, we have to bring in the pure chromium under license and all of this. That of course contributes something like about 82 billion rand to the South African market in its system. Here they talk of chrome ore. Chrome does not exist as a pure metal. It actually exists as an oxide in nature. Very little bit of chrome actually can be found in volcanic tubes, but it's mostly oxides that they do with, which then gets purified through a very complex process, in which then you easily find chrome 6. Now, of course, we have our neighbor Zimbabwe. We do actually buy from them, and we also ship towards them or export towards them, but they're relatively small. Our biggest market is China, of course, in the last couple of years. Now, if you look at just quickly the uses of chromium in this case, I've broken this down in 3 sort of ones. My interest is more the magnetic side, but just quickly, if we look at this chemical here, the majority of leather tanning is done with a sulfide-based chromite. So to actually make this, if you go do the search, most of it, they say, is done by that to soften leather. Then for plastics manufacturing, polyethylene, this is chrome oxide, or a chromite. Actually, chrome within this chemical structure seems to do, there's a structure. It's not, it's sitting actually in the silicon oxide gel, if you do a little bit of the study. But it's mainly to manufacture, this catalyst is used to make plastics, or the base material for plastic. And of course, the pigment beryllium. I see some of my students are here, they'll recognize the nice green color. If you make a mistake in the arc furnace, that's what you get as a result, and that's the end of a sample. And then you 3 days typically down the line when this happens. Then you throw the sample away and you start all over again. And then of course in industry, where mainly chrome is used, also is to make stainless steel. So in this case, depending on how much chrome or nickel you add, you can get 5 different classes of stainless steel. In stainless steel itself, there's something like 100 different grades, broken down primarily in these 5 stages. Depending, do you want stainless that's very high corrosive, non-magnetic, or do you want a very strong stainless? It's a mix. Of course, it's not just a mix of nickel and chrome. It's also a mix of other metals. Sulfur and carbon is sometimes added to a certain percentage. And of course, as I say, my interest or our interest in the chrome research is about the magnetism in this material. It's an antiferromagnet, and we'll come back to that now, what it means for some of the audience. But this lead, and I've shown you a hard drive. There's a breakthrough here that hides here, and this is this GMR, giant magnetic resistance, that actually led to hard drives being smaller. I don't know if those of you coming, say, through the 80s, those computers were quite big things sitting on your desk, and they're noisy when you start up. It's something powering up, and it's crazy vibrating. Well, this GMR, where chrome actually was effectively used within the layer, led to a decrease in the size of this drive, and effectively nowadays, there are now drives with actually no moving parts. But the breakthrough didn't happen here, it didn't happen there, not in the platter where the data is actually stored. The breakthrough actually happened in this little part here that you can't see if you take the hard drive apart. So exploded view, this shows the drive, effectively that bottom end there again, there sits what they call a read-write head, one that reads the data, one that writes the data. But in here sits a tri-layer of iron, chrome, and another iron, where the GMR happens. And we'll discuss a little bit of this GMR. It's quite important actually in our field. This GMR actually led to a Nobel Prize and the development of what's called nowadays spintronics, and the decrease, of course, of hard drives in general, where you don't have moving parts anymore, solid-state devices that we see. So it opened up a whole new field. But if we look at this, what is GMR? Where does this all start? Well, the initial guys who did this is Furt and Grunberg. They discovered it. They won the Nobel Prize, of course, for this discovery in 1988, where the field starts to open. They worked on both iron and chrome and a binary layer and in ternary layer systems. So they stacked them, very thin iron, then chrome, then iron. And they observed what happened if you connect this to a circuit with a battery. Now here's a little light, and you actually want to see. Remember, iron and chrome are metals, so they should be conductive. But in a specific case, now in this case, I've got spins. Now assume these are little magnets sitting in the iron layer, so left to right. That's known as antiferromagnetic coupling, with, of course, there's a chrome layer sitting in between here. You effectively have here a switch in control. So what happens is as the current flow in this antiferromagnetic layer, so chrome sits here with this layer antiferromagnetically coupled, opposite direction and spin, it actually blocks the current from flowing. So you sit here with a high resistivity case. If you then apply a small field on a free layer, so say for example this free layer, that little magnet flips in the iron. What then happens is you now have current flow. That's a low resistive case. The nice thing about it is that the difference here is plus 80%. Effectively, you have a switch. And it's very sensitive to small fields in this case. Okay, now the question is, but where's GMR? I just told you about here, but little magnets, antiferromagnetism and ferromagnetism in this case. Where does this all originate? Well, in actual fact, our simple electron. Well, it's not so simple actually. If you look at it, we assume that the electron is a spilling ball of charge. Those that dig into quantum mechanics will quickly tell you, nah, that's not true. That we just simulate this as a spinning ball of charge. Because it's moving, it produces a magnetic field. And I've drawn two here, or there's two here, and particularly you've got one that shows spin up, you've got a counterclockwise, and you've got a clockwise rotation, spin down. Electrons only come in these two, spin up or spin down, states effectively, with, of course, the associated motion. The other thing is the electrons are spinning, so the charge is spinning, but the charge does not exist alone. In iron or in chrome, this charge is rotating around the nucleus. It's moving. So you've got two motions. First, you've got the charge moving, the electron, that charge moving with its own field, its own magnetism. And you have this electron spinning around the nucleus, so that produces what's called orbital motion. And in things like iron, chrome, nickel, cobalt, this interaction is actually very complex. But most of the magnets actually just rides in effect because of the electrons. They're the ones that, in majority, you see the magnetism. Very important, of course, is for magnets, you need unpaired electrons. Reason being, here I've got spin up, spin down. They sum together, and the magnetism actually sort of cancels out in paired states. So in an orbital, you typically have two electrons if you've got filled orbitals around the nucleus, and that effectively, they do not count. So you need unpaired electrons in their orbits to actually contribute single magnets. So if I quickly just look here, we'll show a little video just to show you GMR. What you have here is effectively you've got current coming in here from the side. Now, a current itself has both spin up, spin down electrons, spin up, spin down channels. So electrons flowing in, a current under electric field. It sees this first ion layer. So the spin down in this case then gets cancelled out or blocked. So if you look at this, so that first layer takes and filters your current effectively in GMR. Now, if you look at the second one here, there a small magnetic field is applied and this free layer now flips. What now happens is, in essence, the current passes through. So you go into a low resistance state, effectively the switch. In spintronics, they actually make what's called spin valves, where you switch the current. So it allows now for control. You've got control in charge, that spinning ball of mass, but you also now have control over this direction, the spin itself. You've got two states to switch in spintronics, for example. So very important breakthrough in chrome. So chrome sits in effectively then in its middle part. Now, let's look a little bit at chrome itself. Now that we have an idea about spins, a little bit of idea about antiferromagnetism, chrome is a body-centered cubic. This is why I say quite a simple crystal structure, five atoms. Here I have already drawn it. These little arrows here is already in the magnetic state, so we'll just talk about how it gets there in 1 minute. But we've got this crystal structure. Now, if I look at chromium here, that's very important in the last orbits. 3d54s1. Remember, we need unpaired electrons to have magnetism to start with. So in this case, there sits unpaired electrons. At the bottom that I've drawn here, or is added, is actually the electronic state of this. Where do these unbound electrons find themselves? Well, firstly, you sit with electron and hole Fermi surface, so virtual surfaces on which these charges are in terms of energy. And in chrome, they can actually move relative to each other. But the importance is that the electron one is smaller than the hole. So when they come together, when magnetism form, one will cancel the other. We call it nesting, in effect. But there always remains a little bit of the surface behind, giving you a positive character to this. Now, in the magnetic state, what happens then? Two things in parallel with chrome. One, you have the shift in the Fermi surface of these two surfaces moving to get nesting. The other is, remember, I have unpaired the electrons already in the paramagnetic state, the random state above where there's no magnetism, supposedly, if we sum over the metal. What then happens, all these spin random are random. As you cool them down, you take energy away. The spins start to align. In this case, I've drawn them that I have the spins on the corner atoms to the left, the center atom orientates to the right. This is antiferromagnetically because you've got left and you've got right. They don't point all in the same direction. Two things, as I said. So you've got spin that starts to form, they start to align, and effectively you've got this gap. And then what happens is throughout the lattice, now we've got one cube structure here, we deal in three-dimensional space. What then happens is you can form a standing wave of these spins traveling through the lattice, not necessarily a single cube. You actually have to stack nearly 21 of these in a row. Then you form this middle picture where you've got the standing wave of about 6 nanometers. It's slightly out of phase with those 21 lattices. And depending on dopants we add, you can shift that in or out of phase, of course with associated properties. Then what's the impact? What do we measure? How do we see what's happening here and what happens in this gap? Of course, one can measure this quite accurately with ARPES. There's a recent paper on chromium where they've done this in Nature. Well, how do we see it in the lab? Well, here is some results that we've measured with our new equipment or with the NEP equipment. This is a very thin layer, 200 nanometers of chrome, very highly orientated substrate because we want a particular direction. And here we show resistivity, so current and voltage with a particular geometry. That's very important. But as you cool down, you take the heat away, and remember two things happen. And this is this little anomaly that you see. And now in chrome, the anomalies are typically very small. You really have to hunt for them in some of the measurements. What happens is, as the Fermi surfaces start to nest, you lose some of the conductors. And thus the slight increase here, where the spin starts to align. Of course, as you cool further, scattering of the electrons become less, and then you get this decrease. The one in red is a Hall measurement, a Hall constant measurement. This tells us something about the charge carriers, the number of them on these Fermi surfaces. It gives you some idea. Again, you come out of the paramagnetic state random. You've got condensation, but now you get left behind with this positive character in the charges. From here, of course, we can always calculate how quickly these charges move, on the surfaces or through the surfaces. Of course, there's another anomaly here. This has got nothing to do with the magnetism. This is known as Umklop scattering that you see in pure chromium. We don't see it in other of the alloys. Now, if we look at, so what else? Now, quickly, I said 45 years. The first paper was actually published by Prof. Alberts, and I think Berger is probably one of his students. This was done in 78. There it is. I took this paper, this first paper, and I just did a quick search, so using Insightful here. Insightful gives you a link. If you've got a single paper, you can quickly cross-link and see how many other papers are tied to this. But this is only one paper. Insightful wants 5. I chose 1. Otherwise, this purple thing in the middle becomes too cluttered. It's too many things on top of each other. So there is the 78 paper, and of course, it spans out. There is a lot of other work, theoretical work on chromium. Chrome was actually seen the first time, the antiferromagnetism, in the 50s, using neutron diffraction. Now, most of the studies between 78 and about somewhere in the 2000s focused on this on the right. So this is a magnetic phase diagram. So remember Tn, if you the curve, we actually track Tn. This is as function of different elements, the non-transitions and the transitional elements at the bottom. They have, because of the electron concentrations, different effects on chromium. The important thing was that most of the work was to track these, what's called triple points in it, where, remember, you have a standing spin density wave in the material over 21 lattices. That those waves can actually rotate in the lattice. And that's what you see here. You see this change into these different spin states. Or you don't call it actually states, but the wave directions. Of course, if you add transitional elements, they actually gave quite high transition temperatures, where the non-transitions, you can see the highest here is 400 Kelvin. But most of the work focused around this. Then when I joined the group, they started working on what's called quantum criticality. We'll deal with this now. But what happens, because you can see here on the x-axis, that's quite low concentrations. Not much work has been done beyond these concentrations. So in this case, I joined the group, my first project after doing solar cells, sort of a crash course into chromium and all the extra measurement techniques you have to learn very quickly. I started working on chrome silicon. I'll come back to what the molybdenum is doing here now. But silicon, together with iron, is the only two elements that actually produce these very sharp transitions. We call them first order. In some measurements, they're actually discontinuous, depending on the quality of your material. But we were tracking what happens if we start following this first order transition. We add molybdenum. Now, why moly? Silicon has the problem, if you add too much, the control closer, this low here starts being problematic. So you can't track certain transitions. We want to track a quantum criticality. What happens when this phase diagram approaches 0? It becomes very sharp. You'll see the data now. So in this case, we have first order. So the molybdenum has the similar Fermi surface effectively than chrome. So it should not affect the chrome magnetically in this case. But it affects it because it affects the interaction between the chrome. So then we can add more molybdenum and we have better control. But the trick is that now this phase diagram or this phase boundary change, this transition changes from the sharp transition to a smooth one, going from first to second order. And there's 2 transition points in this particular sample, particularly if we start tracking what TN is doing as function composition. On the right here, remember this is resistivity, so it's a current applied. You measure a voltage and it's in a particular geometry that's important that we do this. On the right here is the Seebeck coefficient. It is thermal. So what you have is a sample, you apply a small heat, and now the electrons carry the heat through the material. And you don't have this electric current that's doing the work. And again, what you see is the sharp response effectively here, almost first order in the transitions. And then becoming again smooth and quite difficult to actually track at the bottom here. The Seebeck voltages are quite small voltages that we actually measure. But what's the thing here? We do all these experiments, but what are we tracking? We want to track the magnetic temperature to see where you go from this paramagnetic state to an antiferromagnetic state. In this case, so we then go and we plot this after many experiments, many measurements. This only has resistivity on it, but we add the Seebeck to this. We add other measurements to this also. So what we then do is then, if I look at this transition temperature, initially it is linear until you see this almost first order to second order transition here. There's a change in just this slope. What's on the right here is just the magnetic contribution, in essence, to your material. So how strong is this transition at the end? Which you can see is where this first to second order is. But that's not the important one, the funny one. The strange one happens when you approach effectively, it's circled. We've noticed this. So as you add concentration, you see this change. And the question was, why? This is for silicon using molybdenum. Then I worked with Prof. Alberts and worked with single crystals in this case. And on the left here, this gives TN, that ferromagnetic transition, in essence, for the material, as function as composition. But there's a problem. Published work, if you go look at this, that triple point sits in 2 different places. They argue about this. With, of course, these are just incommensurate spin density wave. It's transverse longitudinal. That's the paramagnetic state that becomes commensurate in phase with this 21 lattices over there. We then went and we again measured Seebeck coefficient. We measured heat capacity measurements, how much energy you have to put in to get degree change in temperature. And from that, we could extract this Debye temperature, giving you some vibrational profile. You get gamma, which is the density of state, how many, it tells you something about the electrons or on these surfaces. And then, of course, Hall constant and then carrier concentration. And all of them shows some anomaly around about 2.2% aluminium. We thought, okay, wait a minute. If we look at how deep this triple point sits, the new data seems to suggest that that should actually be the phase diagram. Again, this weird anomaly. Look at this very deep anomaly here, touching in effect 0. So something must be happening. Where here, look, those triple points sits above 100 Kelvin. They don't change. And the question then becomes, but what's going on here? So, and then one very critical thing here, of course, again, we've used aluminium concentration. That's quite difficult to manage experimentally. Theoretically, you can put a little bit in and you can see how a phase change. Experimentally, this becomes very difficult. Okay, so keep that in mind. That's why here you'll only see data points there, and these are all extrapolation of what we think is happening here. They seem to coincide at this bottom point. So before we go in it, just look a little bit at phase diagrams, phase boundaries, things we sort of know of, just to give us a feel. Classical phase diagrams, remember, we are used to water that we cool down, it becomes ice. You boil it, you get steam. When steam happens is dependent on pressure. Very importantly, if I've got a solid, it melts, it becomes a liquid. But what are you doing to this material to get this change from an ordered state to, let's say, a little bit less ordered? Still ordered to some extent, because there's some interaction with the molecules in water, but it's less. Again, you go liquid to gas, okay, but in water, the next one is not possible. You mainly see this in gases. You heat the gas far enough, you get plasma. Our universe is full of this. Okay. Our universe is driven by plasma. Our own sun is driven by this. So what happens? To get these changes in the state, we need to add energy. We add heat. Of course, the reverse is true. And what we do in the lab is we do the reverse. We actually take heat away to see what happens. With us, heat means vibration. We decrease the vibration in the atoms. And that then tells us something, especially when we get to this bottom end. So I just put water here. It itself has a very funny critical point. It's a pressure temperature phase diagram. We are used to water there, water freezing about 272 Kelvin, okay, Kelvin, typically at 1 atmosphere. We are used to water being there. And then you boil water. Here, of course, if you boil, temperature is lower pressure. You have to ask that to an honors student or a postgrad student, and they never can tell you, but why doesn't water here boil at 100 degrees? And then you wonder, what did you do in first year when you teach them? But okay. So on the right here, now, quantum phase transitions. That's what's happening in silicon and this aluminium. Something strange is happening at this point here. So this is magnetization measured. We effectively measure those electrons' little spins, depending on how sensitive the equipment is. Some of our equipment can actually measure down there, not our own, but others in the lab. So you can measure them, and you track the transition temperature as function of a temperature. So Tn in this case, you track it. But then it hits this bottom end here. And that's the funniness. At this point, something else happens to the electrons. Remember, we are studying magnetism, so you're in effect looking at what the electrons are doing. At this minima point here, the electrons actually start acting collectively. They start forming quasi-particles. And then you form what's called a quantum fluctuation and then a quantum critical point. You can think, at 0, no more heat. Heat plays no role here anymore. It doesn't belong. In actual fact, we can track this quantum critical point quite far back in most of our systems. But at this point, heat doesn't play a role. Here, G at the bottom, remember what I told you? We add concentration. We add an element and then you measure concentrations. But in the lab, that becomes difficult to do, to have that fine control. So these are order parameters. Now you can do this as function of magnetic field, but chrome is not that sensitive to magnetic field, so it becomes very difficult to use field. Or you can use pressure. Now some of the first studies on chrome, on quantum criticality, is actually done on pure chrome. Here they've tracked, the authors effectively tracked the null transition by applying pressure, very sensitive, because you can adjust, measure, adjust, measure. They don't, of course, tell you that those are many different samples over a lot of time if you actually dig down into their own data. Because even here it becomes very difficult. The trick is, however, here, where with pressure control you can see there's rotation. This doesn't go on linearly, it actually rotates. And quantum criticality here, where you get this collective behavior, was the first time seen actually in chrome vanadium with vanadium, and then with using pressure that's a lot more sensitive. Doping with vanadium is a lot more chaotic than using pressure in the system. Now, I've shown you about non-transitions, but we also did transition elements, the same as that those first phase diagrams. We actually studied concentrations far beyond 5. The trick, though, in these, in the group 8s, is iridium, rhodium, those, when you add too much, the crystal structure starts to change. So then your magnetism, you're not sure, is it because of the BCC lattice, this body qubit crystal structure, or because you're now studying a different crystallographic phase as another binary in your system. Another way we get around this is we start adding vanadium. Vanadium has got 1 electron less than chrome. It makes the control a little bit easier. The other important thing about group 8s, and there's quite a lot of literature about this, they themselves have superconducting phase transitions, the flow of current without resistance. And we thought, let's see what happens in some of these chrome alloys, because there's contradictory publications on this. And what we found is superconductivity in one of our own alloys, one of our own PhD projects that's sitting here. But the important bit is this. Here are TNs. It's plotted on a log scale, because I wanted to pull it apart. If you plot it on normal scale, it actually compresses a lot of this, and you can't see what's happening here. We want to study what happens here. This gives us, these fits gives us critical constants. It tells us something about the fundamentals happening at these low temperatures. Far beyond this, searching for what's actually happening. What is the electrons doing? Now, on the right, this is where we actually start extracting these critical constants. What we do, again, you do a quick calculation here. Xc is a critical temperature or critical composition where this transition actually goes to 0. So I labeled that one. I left that one extra, and I actually just labeled it to show you we use this concentration. It's quite an important one for us. But the slope of these lines give us these critical constants. I have added here chrome vanadium, which is the first done on chrome, not the chrome pressure one. And then, of course, there's also thin film to see if there's similarities. We do see similarities. We also find these critical constants that tells us something about the mechanisms at the bottom. Then we decided, okay, we've done a lot of phase boundaries over time. Let's study chrome a little bit in something else, Hausler alloys. Spintronics rely heavily on, effectively, these Hausler alloys to make these little spin valves, to make better hard drives, to store more data in less space. We started looking at cobalt-2 titanium aluminium. Why? Well, in essence, this project actually rests on 2 legs as a start. One, it rests in effect on this theoretical calculation of the density of states. Where does the unbound electron sit in an electronic level? Pure cobalt, titanium, aluminium effectively have a little gap. There's a little gap there in the one spin state, and there's another gap here. The material, which is a metal, seems to react almost like a semiconductor. It goes in that direction. Remember, my resistivity curves went flat like this. In this case, the resistivity curve starts to turn up, suggesting there's another mechanism driving most of the electrons of the current flow. So we added chrome to the system. Interesting. And what the chrome does as we add this is actually you lose this semiconductor sort of behavior, semi-metal behavior, half-metal behavior that they sometimes call this. Of course, the work here just shows a crystal lattice. It's quite a complex. They also talk of cubic, but the way the atoms arrange is quite complex. In the system, because of the chrome, initially the system is what they called ordered. Cobalt, titanium, aluminium preferred specific positions in the lattice. The minute you start adding chrome into this lattice, things starts misbehaving. The titanium and the aluminium starts to randomize. And this has quite a big impact, of course, here in the density of states. Also, again, there is a transition temperature to show. These metals are ferromagnets, so they all align. in this case like iron, but when we start adding chrome to it, we can see the transition temperature in this case increases, and at this point, at a 0.75 chrome, it decreases. While the spin moment, the effective moment, still increases, and we're not totally sure. We're still trying to figure this out. There's a lot of questions about why. On the right, just again, back to quantum critical, we study critical constants, most of our materials, because we really want to understand what's fundamentally going on in the system. What you see on the right here is already a calculation, but this is MH loops. So it's the magnetization function of field. And then we extract the initial loop from 0 to maximum field, and then a calculation is done because we're interested in those constants again to see. And we want to drive this that it almost has linear behavior here. And then we study to get these critical constants out of this. And I don't want to show that because it's quite a process to get the data out of this. You measure the data, and then you've got this massive amount of analysis at the end of the day. And then, of course, we had to go further and say, but wait a minute, we've dealt with metals. We've done thin films. I don't have thin films here. Prof. Prinsley did quite a bit of thin films already. So we expanded and we started looking at oxides. Remember, chrome is mined as an ore. Actually, it's iron chromite as an ore that we see. So it's almost natural just to see, but what happens in the oxide itself? Now, the oxide, again, they talk of it's a cubic structure. And if you look at that, that's not cubic. Okay, at first glance. It's actually quite complex. You've got a lot of positions in here that can be filled by atoms. But the chromite actually finds, and the chrome itself, so chrome 6 will sit here, or sorry, chrome 3, at its surrounded by 6 oxygens. And then, of course, if we start adding things like cobalt, nickel, germanium, manganese, and zinc, they will sit in the other positions, in the yellow positions here. But what's the difference now here? The difference here is that if we look at the spin structures, if I take one of these chromes in there, and I start looking at its nearest neighbor, and we start looking at the magnetism, the spin orientation. In chrome, we know they align outer corners in one direction, the inner one in the opposite, to give you antiferromagnetism. Here, these spins actually do not know what they must do. Must I act ferromagnetically? Must I act antiferromagnetically? And it's sums. So what happens in these systems is you then get sometimes a combination of magnetism. If we start adding copper and nickel into the system, you can actually compress these. So those octahedrons, you can start compressing them. In some cases, you get the pull. You now change the distance between the atoms. What happens is the magnetism changes. And that's what this graph here in the figure actually shows you. You have structure change that happens, but these little edges for each metal actually shows different transition temperatures. But also you've got different magnetism here. You go from a ferrimagnet, almost ferro, alignment of spins, same direction, antiferro in other cases. The big thing about that is that you can actually find 2 different magnetisms around the transition point. And we actually had one. This is one of my first masters that I supervised. So in this case, the student used copper and nickel. They're what's called Hunt-Taylor active, meaning in some of the orbitals you've got a split in the energy gap or energy band. And what that does, it actually compresses the octahedron, decreasing effectively the distance, increasing some of your interactions. So this here is just the lattice as we doped with the nickel. You can see it goes from cubic to a tetragonal phase in this case. And then, of course, we extracted, again, the transition temperatures. But the interesting bit is around about, 50, 55, 60, you actually see 2. You see a Curie temperature, and you see antiferromagnetism simultaneously. And then what you find was very exciting. You suddenly find what's called exchange bias, the graph at the bottom to the right. If you go and measure the applied magnetic field and you measure the magnetization, you look at the loop, you can clearly see a shift in the loop. It does not center around 0, like you would expect a theoretical ferromagnet. And we saw this as exchange. Now there's 2 fields here. It's what's called zero field cooled, no field applied. You measure then at low temperature. And the next one you apply field. If you see more of shift, it is a pointer towards exchange bias in the system. This is typically only seen in thin films and has been used successfully in thin films, for example in hard drives, again to use as a switching mechanism. But this is in a nanosystem, a powder. This copper nickel is a powder that we make from liquids in the lab. Another one, and I've added this one on purpose, just to take us a little bit out of the run-of-the-mill. Where we measure magnetization, we measure structure, we measure resistivity and Seebeck coefficients. This one, we still did some of that. We still did the magnetism, but the beauty here is to show our work actually has a biological application on top of this. In particular here, we were studying, or worked together with Wits Medical School. We looked at taking this and see how well this can be used to treat cancer. Will cancer cells die when you add them to a solution where you've got cancer cells? And if you've got live cells, how much of those cells survive? Because remember, they tell us chrome is dangerous. If somebody talks to me and I say work on chrome, a doctor specifically, their eyes go big. You work on chrome? It's dangerous. No, it's not. We've been working on it for 45 years plus. So what this tells us, and again, here we've got chemical, we've got a green synthesis. Green synthesis comes from plant. Aloe vera actually used as a base to make it. The discovery here was that the green synthesized cobalt chromite particles are far better, far worse for cancer. It kills more cancer than what it kills live cells. Okay, here just are the three different compositions, of course, with different doses, meaning the particles themselves in concentration, they change. We chose this. The Wits Medical School studies, these are 6 months worth of studies. It's the first time I've seen how difficult a biological study by itself is to perform. The student had to redo some of their cell work 3 times because the cells got sick. She had to throw them away. And then she starts over again to make the cells. These studies alone are very difficult to do when I listened the first time to her, when she tells us this. But it's the beauty. Our system does work somewhere else as an application. And then, of course, yes. What a mouthful. Ladies and gents, I only took some studies, particular ones where I had a hand in some of the experimental work with students in projects. These are not all the projects that we've worked on over the last couple of years. So some of these studies are difficult. A lot of them have many samples, many studies that you have to put together. It's a very hard process. Our students are sitting here, they can tell you. Experimental work, it's difficult. I feel like this person here, is it a wire problem? And the other one tells, no, there's a little bit more. But can you see something here in this little figure? Does somebody notice something here? Do you think that this person and that person is 2 different people? No. It's the same person. It tells you something weird is going on in this little diagram. I feel many days like this. You only measure 1 sample in a set to discover, you think, I had it, just to figure out, no, you don't. You actually don't, your hypothesis is not totally right, you're missing something. So, yes, I feel many times like this lady here. Now, of course, I have to say thank you. They say to bring a kid in the world, to get them grown up, you need a whole community or family. To do research, you do more. Experimental work particularly. I'm not a theorist, so I can't tell you their perspective. I just know from my perspective, from Aleta's perspective, experimental work demands a lot. I'd like to say thanks to Aleta, many discussions and guidance, mentorship throughout my studies to be here. Prof. Alberts, who's given us a lab when he retired, we've taken it further, we've added equipment, added projects to this. Dr. Andrew Venter, I did not show neutron work here, but we do a lot of neutron work with him. Sometimes we want to study the magnetism, and if you apply field, that transition shifts. They can shift by 5 or 10 degrees on a scale. So the accuracy of that becomes problematic. Neutrons has the nice thing, they don't shift. They interact and you get that magnetic transition with 0 field. NEXA is busy actually, I think Andrew can talk more about that. They're busy looking at a new reactor to advance the research going on there. Then, of course, there are technical people. Eric Rutt, you can see I give him a drawing and then he goes away. After a discussion or 2, he comes back and his is always better than mine. That's the way it works. Theron, he's always there, always ready to help make things. And even when I go back and say, but please can you change this? It's not totally working the way it's designed. He's happy to do that. You can go back a couple, other people not. They get angry at about the 3rd time. Then I want to ask you, but why did you really make this thing? Then Eric Scholes, He's retired, but he's here. But there are many times I have borrowed much from vacuum systems and electronics from him, watching him do things when I was doing my undergrad work. Actually, in my postgrad work, there my masters and PhDs. There were many late nights and your fingers dirty in a piece of equipment. Then Peter Gous retired, but always willing to help. Liani, and then, of course, Mpo nowadays that has to fight, or the interesting one with all the red tape nowadays we have to get through when you want to order something, but by the time you order and by the time there's a lot happened in between in this case. And then, of course, lastly, my family, Zelda, my kids, Tia, Niku, and my parents, of course. I will not be standing here without you. Sorry for that. But thank you for all the support over the years. And then, of course, we have to take away the people who pay for everything. The NEP, our grants, the NEP equipment with its own grant, and that was quite a labor to actually do this and write the reports for so many years continually. But we thank those who supply for experimentalists. We are expensive, like Windows. We are very expensive. Okay, small little thing like this, and you pay 50,000. By no joke. They joke with me typically, I can quickly spend 100,000, and then it's small things. Thank you for that. And then, of course, that's the end, ladies and gents. Thank you. Hopefully that gave you a flavor. It's not all. Okay. Thank you.
Okay, I'm much shorter. Ooh. Okay, this is not working for me. Okay. I did not make slides, but there is slides at the end that I will play because Brian already said that was such a lovely laughing photo of Charles. I've got plenty of those. And there is a slideshow, but that will run at the end. So firstly, I just want to thank Charles for this most insightful address. It was obviously a pleasure for me to listen to the data presented. Prof. Sheppard emphasized the importance of Chromium within the South African context and discussed the history of Chromium-based research, not just at this institution, but also worldwide. As the respondent and scholar in the same field of study as Prof. Sheppard, I wish to comment on this inaugural lecture, highlighting important points. Initial work by Sheppard in the field of chromium research focused on chrome aluminium and chrome silicon doped with molybdenum. This showed very interesting quantum critical behavior. Work on chromium with group 8 elements, such as rhenium, iridium, and osmium, extended the magnetic phase diagrams of these alloys, showing interesting characteristics, including superconductivity. The main driving mechanisms behind the superconductivity are of great interest and were considered. In chrome osmium, that he forgot to highlight, the superconductivity coexists with classical antiferromagnetism, which is very unique. His research highlighted that the simple chromium alloy systems can contribute to a fundamental understanding of superconductivity and quantum critical behavior. Prof. Sheppard was key in the chromium's group's obtaining of the cryogenic measurement system, and this system dramatically extended the group's research capabilities. This allowed us to embark on a new nano project together with our French colleagues at UBO in 2015. Following this, we strategically decided to add the study of chromite-based micro and nanomaterials to the research footprint. Many student projects emanated from this, simulating particles, sizes, magnetic phase contributions, and field dependencies. Investigations on exchange bias continued on core particles and composites, as well as considering the impact of green synthesis methods on the properties of these chromides. In addition, as he highlighted, these compounds can find application in cancer activity research. He also highlighted that we are now looking at Huesler alloys. These alloys can contribute to advancements in spintronics and other technologies. These studies, done by postgraduate students under the guidance of Prof. Sheppard, has revealed many interesting properties, and we are just touching the tip of the iceberg. He alluded to some future research that will focus on thin film work and the production of multi-layer systems through sputtering and liquid-based epitaxy. Through this, we will look at spintronics, and specifically, he was looking to look at spin Hall and the Rashba-Edelstein effects. Spin Hall effects will lead us better into the future of spintronics, which is the vision that Prof. Sheppard has for the group. The significance of Prof. Sheppard's research is broad, promoting the use of chromium in thin films, nano, and bulk forms. The importance of his research work within the broader discipline is clearly evident, with extensions into strong materials, spintronics, and many nano applications. I hope that this commentary on his talk will help you as an audience understand the importance of this new professor's contribution to the research field. In addition, I hope that when you leave this venue, it will promote some discussion that will enrich these proceedings. From my personal reflections on our working relationship, I can affirm that Prof. Sheppard's contribution to the field is highly innovative. I have said many times, Charles is a true physics professor. Not only can he manipulate data, interpret complex data that we obtained from our advanced apparatus, he can actually maintain them. He can build them together with the technical staff. He has built us a complete sputtering system with the help of Eric. How many scientists can actually do that? Think of an idea. I want to make a magnetic film. Go and sit down and make an apparatus to prepare your samples. Charles is truly phenomenal, a rare gem. In a world where people are just chasing the analysis of data obtained from big telescopes, from black box apparatus that they bought, he can actually make apparatus to make the samples and then build apparatus to actually measure what he wants to measure. Now, for me, that is a true physics professor. So I want to express my confidence in your research, Charles. I look forward to seeing your contributions in future to the field of magnetism and magnetic materials. From what you presented here tonight, I am convinced the importance of your work will impact the future. It is truly a great honor to be the respondent at this event. Okay, now I'm emotional. Where's Timothy? Oh, his birthday, guys. Okay, it's truly a great honor to be here, to be the respondent, to formally welcome you as a professor in the academic community at the University of Johannesburg. Now that my duty as respondent is finished, I just want to conclude and say, to my friend Charles, it's a great joy to be here and see you achieve this goal. You advanced from a student to a part-time technical assistant, through countless temporary appointments to a full professor. No one is more deserving of the title full professor of physics than you. Well done. thought the dean is going to do this.
I also thought so.
Yeah, so let me hand
The more the merrier.
let me hand it to the dean.
We can both do it.
No, I feel happy. He's so tall, you can do it.
We can both do it.
Yeah, people always laugh at me. I don't know.
Can we have another big round of applause for Professor? Congratulations indeed, Professor Sheppard. Ladies and gentlemen, we've now come to the end of our proceedings for this evening. But I want to just firstly express my heartfelt gratitude. Where's Berenice? To the team that's organized this event, Berenice and the team. To our media team, to the photographer, the executive dean, Professor Anamotiti, Professor Prenslu, and of course, to our guest of honor today. I want to also thank all of you colleagues and guests for honoring this very prestigious event. And of course, our colleagues that are joining us, colleagues and friends joining us online. So thank you very much. We do have refreshments that will be served to the right of the auditorium. So please join us as we continue with the celebrations. Thank you.